Hi, this is Evans from Crazy Chemistry, and today we're going to speak about dysprosium. Imagine your electric car suddenly losing power, your motors suddenly stop working, not because they're broken, but because they just got too hot. All of this because one element is missing, dysprosium. In this episode, we will explore why dysprosium is critical for high temperature performance magnets, how it prevents magnets from failing, and why is it essential for modern energy technologies. Dysprosium is element 66 in the periodic table. It is a silvery metal in the lanthanide series. Its atomic mass is 162 U, its atomic radius is 178 picometers, and its melting point is 1407 degrees Celsius. Like the rest rare earth elements, dysprosium is found embedded in minerals and rocks such as bastnasite and monazite and can be mined in China, US, and Australia. Its most common oxide form is this one, and its electron configuration looks like this. Like the rest of the lanthanides, it usually prefers forming dysprosium 3 plus ions, which they have electron configuration that looks like this. Dysprosium has many unpaired electrons. These electrons behave like tiny magnets, but unlike many elements, dysprosium remains strongly magnetic even at high temperatures, and this is where it becomes critical. Modern technologies rely on permanent magnets, especially electric vehicles, wind turbines, high-performance motors. The most powerful magnets today are neodymium iron boron magnets, but these magnets have a problem. Even though they're the strongest, they're quite sensitive at high temperatures and they lose their magnetism. This is because thermal energy is disturbing the alignment of their atoms. And when the alignment is lost, the magnet weakens. In extreme cases, they can lose their magnetism completely as well. This is where dysprosium comes in. Dysprosium shows a rare sequence of magnetic transitions as temperature increases. Below 85 Kelvin, which is minus 188 degrees Celsius, it is ferromagnetic, meaning all magnetic moments are aligned in the same direction, producing strong magnetization. Between 85 Kelvin and 179 Kelvin, which is minus 94 degrees Celsius, it becomes antiferromagnetic, forming a helical or spiral structure where the magnetic moments gradually rotate from one atomic layer to the next, instead of pointing directly opposite. Above minus 94 degrees Celsius, which is known as its nil temperature, dysprosium becomes paramagnetic, meaning thermal energy randomizes the magnetic moments completely. A small amount of dysprosium is added in the neodymium iron boron permanent magnets. But even though dysprosium loses its own magnetic order, it still dramatically improves the performance of neodymium iron boron magnets, which typically operate between 300 to 450 degrees Kelvin, which is 25 to 180 degrees Celsius. This is because dysprosium is not the main source of magnetism that comes from iron, but instead it acts like a directional stabilizer. When dysprosium replaces some neodymium in the neodymium iron boron structure, it makes it much harder for the magnetic moments to rotate away from the preferred direction, even when heat is applied. In simple terms, it locks the magnetization in place. This increases the anisotropy field, which tells you how strongly a material prefers to point in one specific direction. From 7 Tesla, it becomes 10 to 12 Tesla. Also, dysprosium tends to sit around the edges of tiny grains inside the material, forming barriers that stop magnetic changes from spreading. This increases the coercivity of the magnets, which is their ability to resist being demagnetized. In simple terms, dysprosium makes the magnet harder to get demagnetized, even at high temperatures. So instead of the magnet demagnetizing, it remains stable. Now, why dysprosium is doing this? Why not any other element? It is because its 4f electrons are extremely localized and they're very stable. The answer is not that it only has magnetic electrons, but it's about how the electrons behave. Dysprosium has a unique electron configuration that creates very strong magnetic anisotropy. That means that the magnetic moments from the electrons orbiting prefer to be aligned in specific direction and resist being disturbed. At high temperatures, most materials lose their magnetism because this alignment of their electrons is being disturbed. But in dysprosium, the electrons are very strongly coupled and therefore thermal energy does not disturb their alignment. They cannot get easily randomized. Dysprosium is also used in nuclear reactors as a neutron absorber in control rods and laser materials because it can interact strongly with both magnetic fields and neutrons. In terms of price, dysprosium oxide is one of the most expensive rare earths, with a price ranging between $300 to $700 per kilogram because it is less abundant and in high demand for modern technology. Dysprosium is working inside motors, turbines, and systems that power modern life. So next time you think about electric cars, remember what makes them work under pressure: dysprosium, an element that allows them to retain their magnetism. So that's it for today. Thank you for watching the video. If you like the video, please consider liking, subscribing, and sharing. Leave a comment if you like. I'll see you next time. Bye.